Hey, we're going to continue today with day 2 of our area problem. So what we did in the previous lesson is we've used a specific number of rectangles to approximate an area under a curve. The issue is that sometimes with these rectangles, there are places that are extra, there are places that are underneath. And so we kind of have that issue of it's either going to be too much or too little or what that's going to be. How could we get a better approximation? Well, what we would want to do is that if we could make these rectangles that we were using, so this is what we did the other day, if we could make these rectangles infinitesimally smaller and smaller and smaller, and then we'd have an infinite number of rectangles, that could better approximate it because then we wouldn't have so much like sticking out or missing from the different pieces, okay? And so what we're going to say here is that the exact area of a plane region, R, is going to be given by the limit of the sum of n rectangles as n approaches infinity, okay? So let's let f be this continuous and non-negative function on the interval a to b. Then the area of this region that's bounded by the graph of f, the x-axis, and those vertical lines x equals a and x equals b is going to be given by this, okay? So this looks like a hot mess, all right? But what we're doing is we're taking the limit of this sum as n goes to infinity. But let me try to kind of spell this out for you. This right here, this b minus a over n, is really our width. It's the width of the rectangles. Remember, the B was where we finished, the A was where we started. So we take the finish minus the start divided by how many rectangles there are. That's the width of each rectangle, right? And so then the other thing that we had yesterday is here we have the width of the rectangle. And then what we're going to do is we have that times like a specific number of rectangles, right? And so again, this is going to be our, like basically the width times I. That's what this part is equal to. This is equal to the width times I. And again, we said that yesterday, for example, well, in the last lesson, we said that we were going to have it for 2/5, for 4/5, for 6/5, etc. And essentially, it was the width times however many rectangles that we were doing, right? And so that's what we're doing. And so what we're doing is we're taking f of the width times I. Now, what's new is this a value. This is our starting value, like in case we don't want to start at 0, okay? And so that's what we have here, but this is the color I'm going to use. This right here, this f of a plus b minus a over n times I, this right here is the height. And essentially what we're doing is we're taking the width times the height, and then we're doing that for a specific number of rectangles, right? So in the last example, in the last lesson, what we did is we had the width times the height, and what we were doing is we were doing that for 5 rectangles. But now what we want to do is we want to do this for n rectangles as n approaches infinity. So what we're going to do is we're going to take the width from I equals 1 to n, and again, our n is going to be approaching infinity, okay? And when we were using a specific number of rectangles, that was the approximate area. But when we're able to use the limit as it goes to infinity, this is going to be the exact area. So we won't need the approximately equal to. And this is because the rectangles, the number of rectangles approach infinity. Okay? So let's start simple and then we'll kind of go from there. All right, so we're going to start with example 6. It says, find the area of the region bounded by the graph of f of x equals x squared, the x-axis, and then between x equals 0 and x equals 1. Okay, so the first thing that let's do, just like we did before, is let's find our width. Okay, our width is going to be 1 minus 0 and then we're going to divide that by the number of rectangles. Remember, we don't have the number of rectangles this time. So what we're going to do is we're going to just call it n rectangles. And so our width is going to be 1 over n. Okay? So there's our width. So now let's talk about the height of our rectangles. Now remember, the height of our rectangles is going to depend on where it hits that graph, right? So what we're going to do is use the function. We're going to use f of x equals x squared. Okay? And remember, this is going to be on 0 to 1. Okay? And so what this 0 tells us, this 0 tells us that this is where we're going to start. Okay? And so what we're going to do is we're going to take the height, again, is going to be f of the starting value, which here is going to be 0, plus the width times I. Our width was 1 over n, and then we have times I. Okay, so again, this 0 right here is where we're starting. Just kind of hang with me for a little bit. And then this part right here is the width times I. And so that's what we're going to want to find. We're going to want to find all of those different function values for our heights. Now, this can really be simplified to f of 1 over n times I, which is really the same as f of I over n. Okay? And so let's actually evaluate that. Let's use the function that f of x equals x squared. And so that means that this is going to be the same as I over n squared. See how I just replaced the x with the I over n? And so then we're going to have I squared over n squared. Okay, so that's our height of our rectangle. Okay, so we've found the width, we've found the height. Now what we want to do is work on finding the area. And so to find the area, this is where we're going to take the limit of the sum of going from 1 to n of the width times the height. I know this says height times the width, but I know the other day we did width times the height. So the width times the height, okay? And then yesterday we had a specific number of rectangles that we were dealing with. But today what we're doing is we're going to find the limit of that sum as n approaches the infinity. So we're taking the limit of the sum of 1 over n times I squared over n squared from 1 to n as n goes to infinity. So let's clean this up a little bit, okay? And that's just, we're not going to use any properties. We're just going to use algebra to rewrite this a little more, in a little better way, okay? And we can just multiply these together, and this can be I squared over n cubed, okay? Now let's think about using the properties of limits, all right? One thing we want to do is pull out the constant. Let's think about what the constant values are. Remember that n is our constant. So what we can do is we can pull out n cubed, this 1 over n cubed, and then we're going to use this I squared. We're going to use our little rules from here, okay? So that's what we're going to end up with here. So we're going to keep the limit as n approaches infinity. Oops, here we go. And then we're going to pull out this constant, 1 over n cubed. But now what we're going to do is use the sum rule for the sum of I squared from 1 to n. And this is where we can use that sheet, okay? And for I squared, what we can do is we can put this in instead. We can say that that's the same as 2n cubed plus 3n squared plus n over 6, okay? And remember, when we use that sum from 1 to n, now the summation goes away. This is if you sum I squared from 1 to n. This is what you end up with. That is the sum. So the summation notation disappears at that point, okay? So then we can just simplify from here. And so what we're going to do is take the limit of, this just ends up being 2n cubed plus 3n squared plus n all over 6n cubed. And again, we don't necessarily have to simplify. This is in general rational form. And so what we know that as n approaches infinity, if our degrees are the same, we can divide coefficients. So that's going to be 2/6, which is equal to 1/3. And so what that means is that my area is equal to 1/3 cubic units, okay? And what's different about this is that this is equal because we were approaching infinity, because we were taking the limit. So when we have a specific number of rectangles, we have to approximate the area. But the cool thing about this method is that it gives us the exact area, okay? So I know we practiced this piece of it before. The new part is this setup, this idea of setting up the idea of the area being the width times the height. And then we're going to take the sum of n rectangles, and then we're going to take the limit of that sum as n goes to infinity, okay? So it's just like a lot of little building blocks put together. All right, so let's try another one. Example 7 says, use the limit process to find the area of the region between the graph of the function and the x-axis over the specified interval. So here we have a new function, f of x equals 1/4 x squared plus 2, and then our interval is 1/4. So let's do the same thing. Let's start with our width. To find our width, what we're going to do is we're going to take 4 minus 1 and then divide by n. So my width for this is going to be 3 over n. Okay. So now let's take my height. And again, because we haven't, we're going to be approaching infinity, we don't need to worry about like what side the rectangles are on. So that's one of the nice things. Again, for the height, we're going to use that f of x equals 1/4 x squared plus 2. And remember, we're on the interval 1 to 4. What that means is that this 1 is where we're going to start. We're not going to start at 0. So our height is going to be given by f of, we're going to start here at 1. And now we're going to add the width, which is 3 over n times I, okay? So again, just a little hint. This is where we're starting. And then this right here is always the width times I, okay? Again, it's strange when we start, but after a little bit, you'll get a little more used to it, okay? So again, what this is representing is this is the x value that we are putting into this function, okay? So what this is really saying is, and we could simplify it from here if you wanted, or you can simplify it after you put it in. I don't know what would be best. Maybe we'll do that. We'll simplify this first and then we'll put it in. So this, if we want a common denominator, this is going to be like n over n plus 3i over n. So what we're really doing is we're going to take f of n plus 3i over n. Okay. And what that means is that we're going to put this in place of this x squared. So that means that we're going to have 1/4 of n plus 3i over n squared plus 2. Okay, so now we just do algebra. So this ends up being n squared plus 6ni plus 9i squared over n squared. So again, just using the square of the binomial. And then we have plus 2. And let's think about what we would want to do. We're eventually going to want to put these together, right? So this is going to end up being, like here, if I put this together, this ends up being n squared plus 6ni plus 9i squared over 4n squared. So that means that we're going to want this to also be written over 4n squared. That's going to be helpful. So we're going to have to multiply by 4n squared over 4n squared. And so that's going to give us 8n squared. So again, this is all just adding rational expressions together, and we end up with 9n squared plus 6ni plus 9i squared all over 4n squared, okay? So again, this represents our height. And so now our goal is to find the area, okay? So again, for our area, what we're going to do is we're going to take the limit of this sum as n approaches infinity. And again, we're taking the sum of the width, which was this 3 over n, times the height, which is 9n squared, plus 6ni plus 9i squared over 4n squared. And again, this is I going from 1 to n. So we're going to take the sum. Again, this is our width. This is our height. When you just look at it like this, it's a little woof, right? But if you think, here's the width, there's the height, it's a little less overwhelming. So we're going to sum that with n rectangles, and then we're going to have the n go to infinity. Okay, so let's maybe make this just into one fraction instead. So I'll just distribute this 3. So I have 27n squared, 18ni, 27i squared over 4n cubed. Okay. Now we know we want to try to use the properties of limits to break this down a little bit. So I'm going to take this limit out, and then I'm going to deal with all of these sums separately. Okay, so first of all, I'm going to deal with the sum of this 27n squared over 4n cubed from 1 to n. Now I'm going to deal with the sum of 18ni over 4n cubed from 1 to n. Now I'm going to deal with the sum of 27i squared over 4n cubed from 1 to n. Okay, so again, just using the properties of limits to kind of like separate each term so that I can use our properties. So the first thing we see is that this is a constant. So that means that we can use this rule here. We can take the constant times n. So our constant is this 27n squared over 4n cubed. And so now we're going to multiply that times n. Okay? Plus, this time we're going to pull out our constant, which is 18n over 4n cubed. Okay, but we have this I that's here. And so what we're going to do is use the rule to take the sum of I from 1 to n. And that's where we're going to use rule 2. So this is where we're going to have n squared plus n over 2. Next, we'll pull out another constant. That constant here is 27 over 4n cubed. And now I need to take the sum of I squared from 1 to n. And the sum of I squared from 1 to n is going to be this, 2n cubed plus 3n squared plus n. And again, it is nice that we've fleshed them out and distributed so that we don't have to worry about that in our steps. If you're like, well, why did we take these out here and we didn't here? I mean, we really did, you guys. You could really think about this as like a 1 here, and then the 1 is what gets replaced with the n, but like that's essentially what's happening. We're pulling out the constants and then using the different rules. Okay. Okay, so now the magic is done as far as using our summation properties and our formulas. And so now we're just going to look at simplifying each of the terms to clean it up a little bit. So this would give us 27n cubed over 4n cubed. This gives me 18n cubed plus 18n squared over 8n cubed. And this gives me 54n cubed plus, what's that, 81n squared plus 27n over 24n cubed. Okay? So, I know that I could make a common denominator, but I'm going to get kind of, I don't want to say lazy, but I'm going to know that I can actually take, using the properties of limits, I also could just take the limit of each of these and add them up, right? And then worry about the denominators later. So let's do that, you guys. Let's take the limit of each of these. Let's take the limit as n goes to infinity of this piece. Notice the degrees match. So this part is just going to be 27/4. We take the limit of this term, the degrees match, so this would be 18/8. Here, take the limit of this piece, the degrees match, so that's just 54/24. And so if we add these together, oh, I should have brought a scientific calculator. It doesn't matter too much. But if I take 27/4 plus 18/8 plus 24/24, that gives me 11.25, which is 45/4. And if it's a terminating decimal, that's fine too. And so that is our area. My area is going to be 45/4 square units. But essentially, you guys, this is the process that we're going through, okay? It's just like legit over and over and over again. That's what we're doing. Again, it looks a little messier than it is. The newest part for today is the setup part, okay? Let's just try this again. Again, like the more we do this, hopefully the more it'll kind of like click in, okay? So example 8, find the area of the region bounded by the graph of f of x equals 3x minus x squared, the x-axis, and between x equals 1 and x equals 2. Well, guess where we're going to start? We're going to start with the width. For the width, I'm going to take 2 minus 1 over n. And again, I don't need to see that work. If you just want to write 1 over n, that's great. Okay? Now, I need to think about what my heights are going to be. Remember, for the heights, I'm going to use this as the rule. And essentially, I'm going to take f of the start value and then plus the widths, okay? And the reason we need the start value, because if we just had, like if we just put the width, that means that we'd be starting at 0. But we don't want to start there. We want to start over here. We want to adjust it, basically like shift it over that 1, okay? So again, our start value is 1 plus our width was 1 over n, and then we're going to multiply that times I, okay? So again, remember that this was my start value, and then this was the width times I. It's been that way every time, okay? So, okay, so here we can think about that as n over n, and so this could be n over I over n, and that works, okay? And then what we can do is we can start substituting that in here. So this is going to be 3 times n plus I over n minus n plus I over n squared. And essentially this is just where we're going to deal with the algebra. Okay, so If I distribute here, that's going to be 3n plus 3i all over n minus, this is going to be n squared plus 2ni plus I squared over n squared. Okay. And now to make common denominators, I see I'm going to have to multiply this by n over n. So this is going to be 3n squared plus 3ni. And then just let's just, I'll put it in one here, but let's just make sure that we're distributing this negative everywhere as well. So we're going to have minus n squared minus 2ni minus I squared, and then all of that is going to be over n squared. So that gives 2n squared plus ni minus I squared over n squared. Okay, so that represents the height of the triangle, or wow, of the figure. It's not a triangle. All right, so the next thing we're going to do is look at our area. And remember, for our area, we're going to take the limit of the sums of the areas as n approaches infinity. So again, we're going to take our width times our height. Okay. So we're going to take the limit of this area, the width times the height, from 1 to n as n goes to infinity. Okay. And once again, I'm just going to point out that this is our width. This is going to be our height. Okay. All right. So working on that, we can see that this is going to be just turning it into, like, multiplying the width and height together. We're going to have 2n squared plus ni minus I squared over n cubed. And then this is where we can break it down into the different pieces. Okay, so I'm going to think about taking the sum of 2n over n cubed from 1 to n. Oops. I'm going to thinking about taking the sum of ni. Okay, sorry guys, I ran out of disk space, so I think it cut me off for a little bit, but hopefully you can see where I left off. So anyway, so I'm going to take the sum of 2n over n cubed from 1 to n, ni over n cubed from 1 to n, and then I squared over n cubed from 1 to n. Just to notice that because I'm subtracting, then that's going to be a subtraction sign that's here instead. Okay, so now at this point, this is where I use my summation formulas sheet, and I am going to deal with these different pieces here. So again, this was a constant that I'm going to multiply by n. Here my constant was n over n cubed. And now I'm going to multiply by, again, if you need me to circle this, the sum of I from 1 to n, which is n squared plus n over 2, minus. Here my constant is 1 over n cubed. But now I'm going to use the sum of I squared from 1 to n, which is the 2n cubed plus 3n squared plus n all over 6. All right, so then again, let's just look at each of these terms. This is going to be 2n cubed over n cubed. This will be n cubed plus n squared over 2n cubed. This is going to be 2n cubed plus 3n squared plus n over 6n cubed. Okay, and then we can just take the limit of each of these pieces. So this is going to be 2 plus 1/2 plus, just kidding, minus 2/6, okay? And we can put that in the calculator. This isn't too bad. I'm just going to make common denominators for these here. So with a common denominator of 6, 1/2 turns into 3/6, 2 turns into 12/6. So 12 plus 3 is 15, minus 2 is 13/6. And so that's going to be my area. My area is going to be 13/6 square units. Okay? So again, nothing really new. It's just, I'm just trying to do these examples so this clicks in for you as far as that's process. Okay? Let's do one more. So this time we're going to find the area of the bounded region. Here we can tell that it's going from -1 to 2. And this curve is given by 3 minus 1/4 x cubed. Okay, so we'll start with our height, just kidding, with our width. And our width is 2, because that's where that vertical line is, minus -1 over n. So our width is going to be 3 over n. And our height is going to happen at f of our start, which is -1, plus the width, which was 3 over n, times I. Okay? So we could rewrite that as -n plus 3i. I don't like negatives first, you know me. 3i minus n over n. If you write it as -n plus 3i, that's beautiful, okay? Excuse me. And so now we're going to have to put this in here. Can you see why this might be a little annoying? Yes, because we're cubing. Okay, so we end up with 3 minus 1/4, and now we're going to want 3i minus n over n cubed. All right. So we've got 3. And so again, the annoying part isn't the calculus for this, it's the algebra. But we love algebra, so it's going to be okay. All right. So if we cube this, remember that there's that pattern of cubes. Do you remember that pattern? That if you have a minus b cubed, that's going to be a cubed minus 3a squared b plus 3ab squared minus b cubed. And then if it's a plus b quantity cubed, then they're all addition. It's a good one. It's a good one to remember. So let's use that. And so if I take this, I'm going to think about this as my a. So 3i cubed would give me 27i cubed. Okay. Now I'm going to take 3 times 3i squared times n. So that's going to be 3 times 9i squared, so 27i squared times n. So minus 27i squared n. Now I'm going to have 3 times a times b squared, so 3 times 3i times n squared, that's going to be 9i n squared. And then minus cubed, so minus n cubed. And then this is over n cubed, because I'm going to cube the numerator, cube the denominator. Okay. All right. When I rewrite this here, remember that n is the constant. So I wrote this as I squared n because of the order it came, but really like 27n is going to be the coefficient I'm going to pull out. So I can see that my denominator here, I'm going to need a 4n cubed. So I can multiply this by 4n cubed here, and this is going to give me 12n cubed. And then I'm going to have minus, just write this all out here, minus, we'll have 27i cubed. I'm going to apply this negative to each one of these, okay? So this is going to end up being plus 27, and I'm going to rewrite this as ni squared. Then here this is going to be minus 9. I'm going to write that as n squared I, and then plus n cubed. And then all of this is going to be over 4n cubed. So this will be 13n cubed minus 27i cubed plus 27ni squared, oops, minus 9, oh shoot, n squared I. Sorry. Okay. I had too much of a space here. All right, so now let's find the area. My blue is running out. I'm going to use a different blue for this area. So again, my area is going to be the limit of this sum. And again, the sum is going to be my width times my height, which I can nicely rewrite now that I have a little more room. Okay, so 13n cubed minus 27i cubed plus 27ni squared minus 9 ni cubed. Yes, okay. No, 9n squared I, geez, over 4n cubed. Oh, and then don't forget this is I goes from 1 to n. Okay, so I can multiply this, the limit, and let's just turn this into one value. This is going to be 4n to the 4th. And then this is going to end up being 39n cubed minus 81 I cubed plus 81 ni squared minus, oh, here we go again, 27 n squared I. think I kind of made it. All right. And then we can separate those out into different pieces. So I have the limit of these different sums. So I'm going to take 39n cubed over 4n to the 4th. Oops, this is an I. Going from 1 to n. Minus, I'm going to take 81i cubed over 4n to the 4th from 1 to n. And then take 81 ni squared over 4n to the 4th as I goes from 1 to n. And then, oops, subtract 27 n squared I over 4n to the 4th as we go from 1 to n. Okay. So now at this point, this is where we use the summation piece. Okay, so we still have this limit, but now we're going to get rid of the summation part. Here we're going to have my constant 39n cubed over 4n to the 4th times n minus. We're going to have this 81 over 4n to the 4th. And now we get to use our rule number 4. So when we are taking I cubed from 1 to n, this is where we end up with n to the 4th plus 2n cubed plus n squared all over 4. Now I'm going to pull out this constant, 81n over 4n to the fourth. And now I'm going to use my rule for I squared. Again, 2n cubed plus 3n squared plus n over 6. Now I'm going to pull out this constant, 27n cubed over 4n to the fourth. And then use the rule for I, which was n squared plus n over 2. Okay. And so now we just keep going from here. So again, I like to simplify each one of these. So 39n to the fourth over 4n to the fourth. This ends up being 81n to the fourth minus 162n cubed. Oh, I should say plus 81n squared, since we're not combining like terms, over 16n to the fourth plus 162n cubed plus, what's that, 243 n squared plus, just kidding, this is n to the fourth. N times n cubed is n to the fourth. N times n squared is n cubed. And then 81n times n is 81n squared. And then this is over 24, n to the fourth, minus. And then I have 27n to the fourth plus 27n cubed all over 8n to the fourth. Okay. And again, at this point, like, to be honest, in a quiz test situation, I kind of do want to see this, and then I can just kind of see where you're at. But the next step, the only thing I worry about is taking the limit, right? And so this gives me 39 fourths. This gives me 81 sixteenths. These match. That's 162 over 24. These match. That's 27 over 8. And if we put those together, 39 fourths minus 81 sixteenths plus 162 24ths minus 27 eighths. I end up with 129 over 16. And so that is my area, 129 over 16 square units. So that way, if anyone asks you this question, you could get off a desert island by doing this process, right? This is really a precursor to what you guys are going to be doing in calc, which is called integration. Again, sadly, it's my job to teach you the kind of tedious theory behind it. But then next year, you guys will learn some shortcuts. Okay, so if you learn shortcuts from your friends, just know that on your quiz test stuff, I do want to see the limit process. And that's why on the test, it'll say something like use the limit process. Okay, so this next example, hang on. I'm sorry to clear my throat. So in the next thing, I do want to show you, you can't use a graphing calculator on the test, okay, for this part of it. But I do want to show you how to use the integrate feature on the graphing calculator to help you find the area of the region between the function and the x-axis over the specified interval. So let's say that we wanted to do that for this particular function that was right here, okay? I know that's not on your page. But what we're going to do is you're going to go basically, what you can do is you can hit alpha. In the newer models, you can go to alpha window number 4, okay? But you can also go to math, and then you can go over to this where it says INT, FNINT number 9, and you're going to get something that looks like this on your screen, okay? This number down here is where you start. This is where you stop. So if we're doing this, we're starting at -1 and we're stopping at 2, right? And then we're going to put our rule in. Our rule is 3 minus I'll put 0.25x cubed. Oh, shoot, I'm in the wrong mode. Let me go back to function mode. Here we go. There we go. Sorry, I was in function mode. Or in a parametric mode, polar mode. So I had to put it back in function mode. So I got that x back. And then this is what it's with respect to. So we're just going to put dx since that was it. So if you had a theta here, you could have a theta here as well. But notice that it gives us that answer that we just got in a fraction of the amount of time, no pun intended. But again, this is the theory. Again, it's like this is so nice that you'll be able to do this really quickly, in the future. But again, this is the theory. This is what the calculator is doing. Isn't that amazing? You're just as good as a calculator, you guys. So if you did have something like this and we wanted to do that, if we wanted to find this, if we were to do example 10a, we could then go to math number 9, or again, the alpha window number 4. We would want to go from 0 to 3. And the rule that we're doing is 3 minus x root x. And then we have dx. And then we can see that's going to be about 4.157 units. Square units, I should say. Okay. So then for this next one, math number 9, this time we're going to go from 0 to 2. Oops, I need to put in some rules. And then 6e to the negative x dx, and that gives us about 5.188 square units. Okay, but again, because I love your brains, no graphing calculator on your tests, okay? But it's something you can do to check your answers on your homework if you don't want to look at the other pieces there, okay? That's the scoop. So I hope you guys enjoyed that. Sorry about the work, but it's good for you. It's good to get this theory out of the way so you can learn your shortcuts next year, okay? Congrats. Have a great day.